Welcome to today's session. In the previous class, we were looking into linear programming and formulation of linear programming. In this session, we had seen what is linear programming and we saw what is actually formulation of linear programming. So after looking into simple problems on formulation of linear programming, today we'll be looking into problems with little more complexity, wherein all the content are not directly given. We may have to perform a small amount of computation before we will be able to formulate. So, shall we start off with the problems? The first problem: a manufacturer of packaging material manufactures two types of packing tins. One is of type round, other one is of type flat. Major production facilities involved are cutting and joining. So to manufacture round tins and flat tins, he has two jobs to do. One is cutting, other one is joining. The cutting department can process 300 tins of round or 500 tins of flat per hour. So this word per hour is important. We will discuss it later. The joining department can process 400 tins of round or 300 tins of flat per hour. If the profit contribution of round tins is rupees 100 per tin and that of flat is rupees 80 per tin, formulate the LPP to maximize the profit. So this is the problem given. So we will see what are all the decision variables and we will write the given data in a tabulated format. The decision variables are two decision variables because we have two types of materials. One is round tin, other one is flat tin. So decision variable will be number of units of round tin produced, x2 number of units of flat tin produced. The given data, we'll just make a note. The profit for round tins is 100 rupees. Profit for flat tin is 80 rupees. Here we have not been given the time constraint, but they have specified per hour manufacturing abilities. So we need to assume that the total duration given to us is 1 hour. So with respect to cutting, for round, we are able to manufacture 300 tins per hour. Cutting of flat tins, 500 tins per hour. Similarly, joining 400 tins per hour for round, 300 tins per hour for flat. And the maximum duration that is available with us, we are going by the assumption because it is not specified and they have very clearly mentioned in the problem that it is per hour manufacturing. So we assume 1 hour to be the maximum duration available for cutting and the maximum duration available for joining. So now let us look at how the objective function would be. Objective function very much similar to all the previous problems that we saw. Z is equal to 100 x1 plus 80 x2. 100 is the profit for per unit of round tin. 80 is the profit per flat tin. Fine. Coming to the cutting constraint. So it is 300 tins per 1 hour. So therefore, the number of units that you manufacture will be a fraction because for one round tin to be manufactured, the time duration is 1 by 300. because for 1 hour we are manufacturing 300 tins. For 1 tin, the duration is 1 by 300. Therefore, the constraint will become x1 by 300, and for flat, it is x2 by 500, and it has to be less than equal to 1. Similarly, joining constraint will be 400 and 300. So x1 by 400, x2 by 300 less than equal to 1. And x1 and x2, it is the number of tins produced, so it cannot be negative. So non-negativity constraint says x1 comma x2 greater than equal to 0. So the final solution will look like max 100x1 plus 80x2 subject to x1 by 300 plus x2 by 500 less than equal to 1, x1 by 400 plus x2 by 300 less than equal to 1, x1 comma x2 greater than equal to 0. I hope you have understood the problem. Here, the key of solving the problem here is they have given us the abilities of processing 300 tins or 500 tins per hour, and similarly here 400 tins or 300 tins per hour, but the total duration available is not given. Because the total duration is not given, we are assuming the total duration to be 1 hour. Therefore, individually in the constraints, it will become 1 by 300, 1 by 500, 1 by 400, and 1 by 300. Is the concept clear? Shall we move on to the next problem? So, the next problem that we consider here, have a look at the problem. A medicines manufacturer proposes to prepare a production plan for medicines A and B. So two types of medicines are being manufactured, medicine A and medicine B. There are sufficient ingredients available to make 30,000 bottles of medicine A and 50,000 bottles of medicine B. So here the availabilities are given with respect to individual medicines. See, with respect to the production, they are not giving the availability. The key of this problem is the availabilities are given individually with respect to a particular finished product. For machine A, 30,000 bottles is maximum. For medicine B, 50,000 bottles is the maximum. Fine. We'll continue with the problem. But there are only 40,000 bottles in which either of the medicines can be filled. So individually, maximum that you can manufacture for A is 30,000. Maximum that you can manufacture for B is 50,000. But to fill this, the maximum number of bottles that are available with us are only 40,000. So this is a separate constraint altogether, which is a bottling constraint. So the number of units of medicine A that you have manufactured and the number of units of medicine B that you have manufactured, when you add them together, it cannot exceed 40,000 because we have only 40,000 bottles. Clear? Next, shall we continue with the problem? Further, it takes 4 hours and 3 hours respectively to prepare enough material to fill 1,000 bottles of medicine A and medicine B respectively. And there are only 70 hours available. So this is very much similar to the constraint, basic constraints that we were looking at in the earlier simple problems. So 4 hours is required for manufacture of 1,000 bottles of medicine A, 3 hours for 1,000 bottles of medicine B. Total duration available with us is 70 hours. Now coming to the profit part of it, The profit is rupees 9 and rupees 6 per bottle of medicine A and medicine B respectively. Formulate this as an LPP. Fine. Let us look into what is the objective and how we tabulate the given data. So the decision variables are obviously two decision variables because we are manufacturing two finished products, medicine A and medicine B. So X1, I'll consider it as thousands of bottles of medicine A produced. X2 is thousands of bottles of medicine B produced. Now you might get a doubt, why not number of bottles? Why thousands of bottles? Because in the problem they have very clearly mentioned that we are manufacturing 30,000 bottles here 50,000 bottles, 40,000 bottles, and the duration is also given in terms of 1,000 bottles. Therefore, when the problem is considering the units in thousands of bottles, our decision variable will also be in thousands of bottles. So we will have a look at the given data. Profit rupees 9 and rupees 6, but it is rupees 9 and rupees 6 per bottle. But the unit that we have considered is 1,000 bottles. Therefore, 9 into 1,000, 9,000. Profit for medicine B, 6 into 1,000, 6,000. Fine. Coming to the time constraint, 4 hours for medicine A, 3 hours for medicine B. Total duration available is 70 hours. Okay. Now coming to the bottling. See, here total number of bottles available with us is 40,000 bottles. And the number of thousands of bottles that you manufacture, we are supposed to take a sum of it. That is x1 plus x2. So the coefficient is negligible here, or we are not interested much in the coefficient here. Therefore, I assume the coefficients to be 1 and 1. So 1 into x1 plus 1 into x2 should be less than equal to 40, right? Number of thousands of bottles of medicine A plus number of thousands of bottles of medicine B should be less than equal to 40,000 bottles. Clear? Now coming to the availability part that we saw here, individual maximum availabilities. So I am specifying it availability which are individually mentioned. Medicine A maximum 30, medicine B maximum 50. So how do we write it as constraints? We will just have a look now. The objective is obviously to maximize the profit. So the objective function would become z is equal to 9,000 x1 plus 6,000 x2. Constraint will be the first time constraint is very much similar to whatever we have done till now. 4x1 plus 3x2 less than equal to 70. Bottling constraint also very much similar to the earlier constraints. X1 plus x2 less than equal to 40. Now the new one that we have observed is medicine A availability constraint, individual constraint. X1 should be less than equal to 30. That is maximum number of thousands of bottles that you produce for medicine A should not exceed 30,000. Fine. Sorry, there's a small typing mistake here. This has to be medicine B. I copied and pasted. Editing, I forgot. So it should be medicine B availability constraint. Medicine B maximum you can manufacture only 50,000. So X2 less than equal to 50. And the number of thousands of bottles that you manufacture cannot be negative. Therefore, non-negativity constraint will be x1, x2 greater than equal to 0. Now, combining all these constraints, how do we write the LPP? We will just have a look. The solution will look like max z is equal to 9000 x1 plus 6000 x2 subject to 4x1 plus 3x2 less than equal to 40, x1 plus x2 less than equal to 40, x1 less than equal to 30, x2 less than equal to 50, both x1 and x2 are greater than equal to 0. Hope the concept is clear. The new concept that we have seen in this problem is individual constraints or individual limits being given. So we'll have a look at the next problem, which is bit more complex. So we will just have a look at the problem now. A company has two grades of inspector, 1 and 2. That is, we have two types of inspectors, grade 1 inspectors and grade 2 inspectors, who are assigned for a quality control inspection. It is required that at least 1800 pieces should be inspected per 8-hour day. That means to say, in one day, both grade 1 and grade 2 inspectors together should should check at least 1800. That means to say it should be greater than or equal to 1800. It should be either equal to or should be greater. When I use the word at least, it means it has to be greater or equal to. Continuing with the problem, grade 1 inspector can check pieces at the rate of 25 per hour. He can check 25 pieces in 1 hour with an accuracy of 98%. Grade 2 inspector can check pieces at the rate of 15 per hour with an accuracy of 95%. The wage rate of grade 1 inspector is rupees 4 per hour, while the wage for grade 2 inspector is rupees 3 per hour. So here per hour wages are given. Each time if an error is made by an inspector, the cost to the company is rupees 2. So for every mistake, rupees 2 is cut by the company. The company has 8 grade 1 inspectors and 10 grade 2 inspectors for the inspection job. So this sentence is giving us individual limits. I have only 8 grade 1 inspectors. I have only 10 grade 2 inspectors. So these are individual limit constraints. The company wants to determine the optimal assignment of inspectors, which will minimize the total cost of the inspection. Till now, in the earlier problems, we were talking in terms of profit. Profit is one which has to be maximized. A variable like profit, a variable like discount earned, these have to be increased. There are variables like the duration or time taken for a particular job. No one would be interested in increasing the time for a particular job. We are supposed to decrease the duration. We talk about cost. No one will be interested in increasing the cost. Cost is a variable that has to be minimized. So this is common sense. I hope we have it, right? Common sense is one thing which we are supposed to have. Most of us keep it safe and we don't use it. Clear? So here we are supposed to look into the variable. If the variable is talking in terms of profit, then it has to be maximized. If it is talking in terms of cost, cost has to be minimized. So they need not specify in the problem that you are supposed to minimize the cost or maximize the profit. If at all they don't specify also, using your common sense, you should know whether the problem is maximization type or minimization type. But anyhow, in this problem, they have very explicitly specified that it is minimization problem. So you are supposed to formulate an LPP to minimize the total cost of inspection. So we will just have a look at what are all the decision variables. What should be the decision variables? Obviously, we have two different types of inspectors and we are supposed to determine the number of inspectors that are being assigned for the job, right? So you will have two variables, two decision variables. X1 will be the number of grade 1 inspectors being assigned. Then X2, that will be the number of grade 2 inspectors being assigned. So we will have a look at it now. Decision variables, number of grade 1 inspectors to be assigned. X2, number of grade 2 inspectors to be assigned. Clear? Now, given data in terms of cost. See, this is the complex part that I said. See here, 4 rupees is the wage per hour, right? For every 1 hour, the wage is 4 rupees. So 4. And 2 rupees is being cut for every mistake. So how many pieces he is checking for 1 hour? 25 pieces. How much is being cut? 2 rupees. How many mistakes he is doing? If it is 98%, 98% can be written as 0.98. So how many mistakes he is doing? 0.02. Out of 100, 98 is subtracted. 2% mistakes he is doing. 2% can be written as 0.02. That is what we have done here in the calculation. 0.02 into 25, right? Number of pieces into 2 rupees. So this is the cost that is incurred by the company. So 4 rupees is the wage that is given, and this is the extra amount that the company spends for every mistake he does. So this altogether will be 2 into 25 is 50, 50 into 0.2 is 1, or 0.02. 50 into 0.02 is 1, 4 plus 1 is 5. So this is for 1 hour, and they have specified it is on a 8-hour day. So 8 hours they are working. So this 1 hour cost, whatever is incurred, has to be multiplied by 8 so that it gives us the total cost. So 5 into 8 is 40. Similarly, 3 rupees is the wage for grade 2, 2 rupees is the cost, and the number of pieces that he inspects is 15, and the error that he makes, because his accuracy is 95%, 5% is the error. 5% can be written as 0.05. So 0.05 into 15 into 2. That is 2 into 15 is 30. 30 into 0.05 is 1.5. So 3 plus 1.5 is 4.5. So for 1 hour it is 4.5. So for 8 hours it will be 8 into 4.5, 36. Okay, this is the cost computation. This is the key part that we are supposed to look at. And the number of pieces that they are checking in 1 day. The constraint given to us is maximum they are supposed, sorry, minimum they are supposed to check 1800 per day. How much they are able to check? 25 per hour. So in 8 hours, So it is 8 into 25 and 8 into 15. So that is what we have done here. 8 into 25, that is 200. Grade 1 inspector can check 200. Grade 2 inspector can check 8 into 15, 120. So when we add these two, it should be greater than or equal to 1800. Then individual availability constraint, maximum grade 1 officers that we have is only 8. Maximum grade 2 inspectors that we have is 10. So now we'll look at how these constraints are individually written. So the objective is to minimize the cost. Z is equal to 40x1. 40 is the value that I have got here, and 36 is the value that I've got here. So therefore, Z is equal to 40x1 plus 36x2. Okay, coming to the constraints part, the number of pieces constraints. 200 can be inspected by inspector 1, 120 by grade 2 inspector. So 200x1 plus 120x2 should be greater than or equal to 1800. Okay, then we have grade 1 inspector constraint, which will be x1 less than equal to 8. Grade 2 inspector constraint, x2 less than equal to 10. And the non-negativity constraint, the number of inspectors cannot be negative. Therefore, x1 comma x2 greater than equal to 0. Hope the concept is clear. Now, finally, how we are writing it as an LPP. Min Z is equal to, because it is minimization problem, we are writing min Z equals 40x1 plus 36x2 subject to 5x1 plus 3x2 greater than equal to 45. Now you have a big question mark. How did this 200x1 and 120x2 and 1800 become 5x1 plus 3x2 greater than equal to 45? I have just minimized it, right? Divided it by a common factor. So we get 5x1 plus 3x2 greater than equal to 45, x1 less than equal to 8, x2 less than equal to 10, x1 comma x2 greater than equal to 0. Hope you have understood the problems for today. Thank you. Have a nice time. Enjoy. Bye.